Hello everyone, welcome to my channel ECE Scholastic. I am Jasmine. We have started a series of sessions under the topic Frequency Response Analysis. In the previous session, we have discussed what are the basic concepts behind this frequency response analysis. In this session, we are going to see what are the frequency domain specifications and the explanation with respect to representations. Okay, so let's start the session. First is frequency domain specifications. So for a system, the performance and the characteristics in frequency domain is measured with the help of certain parameters, which is called as frequency domain specifications. So the frequency domain specifications are resonant peak represented as MR, resonant frequency represented as omega R, bandwidth represented as omega B, cutoff rate, gain margin kg, and phase margin gamma. So let's see all these specifications in detail. With the help of this diagram, I can explain what is what in the frequency domain specifications. So here we have a representation MR. MR is nothing but resonant peak. And we have one more term, that is omega R. Omega R is resonant frequency. BW is the bandwidth. Omega is called as the frequency in radian per second. Correct. And this modulus of m of j omega is nothing but magnitude, or in other words we can say it as gain. So gain is usually represented in decibel, okay, dB. Okay, so resonant peak is nothing but the maximum value of magnitude of a closed loop transfer function. Okay, so this resonant peak represents the relative stability of the system, and the range of this resonant peak will be from 1.1 to 1.5. Okay, if MR value increases, then we can say the peak overshoot value also gets increased. Okay, so that we can say MR is directly proportional to this peak overshoot. Next is resonant frequency. So resonant frequency is the frequency at resonant peak value, and this indicates the speed of the transient response. So this is called as transient response. So the speed of the transient response is indicated with the help of this resonant frequency. Okay. Next is bandwidth. What is the basic definition for bandwidth? Bandwidth is the difference between upper cutoff frequency and lower cutoff frequency. So in order to find the upper cutoff frequency and lower cutoff frequency, we need a cutoff rate, correct? So we are going to consider the cutoff rate to be minus 3 dB. Okay, why we are considering this minus 3 dB as the cutoff rate? The output power will be 50% of the final value, so that we can say that this is the maximum tolerance level. In order to find this upper cutoff frequency and lower cutoff frequency, we have to take a 3 dB bandwidth from the resonant peak. Okay, in other words, we can explain bandwidth as the ability of the system whose output reaches half the input within the accepted tolerance band. Okay, let's see what is a cutoff rate. So what is a cutoff rate? Let me explain with the help of this diagrams. On analyzing this graph, we can say that from 0 dB, okay, and from the frequency 0.001 to 0.1 radian per second, we are getting a flat response. Okay, so within this 0.1 to 1 radian per second, the response starts to decrease linearly, correct? Frequency at which the response starts to increase or decrease from a steady value is called as the cutoff frequency. And the slope drawn at this cutoff frequency is called as the cutoff rate. Okay, in other words, we can say at cutoff rate we differentiate the signal from the noise. Okay, so on seeing this diagram, you can say what is a bandwidth. So I have drawn a response. So from this response, I have taken a 3 dB bandwidth from the resonant peak. So this is our resonant peak value, and this is our resonant frequency. Correct. On taking 3 dB bandwidth from the resonant peak, I am getting two frequencies, F1 and F2. F1 is called as the lower cutoff frequency and F2 is called as the upper cutoff frequency. So the distribution of energy between this lower cutoff frequency and upper cutoff frequency is called as bandwidth. Why we are using this minus 3 dB? Because this is the maximum tolerance level for the bandwidth. That is, at this point, our output power will be 50% of the final value. Okay. Next, let's discuss what is gain margin and what is phase margin. So gain margin is represented with the symbol kg and phase margin is represented with the symbol gamma. Okay. So gain margin is the tolerance gain value given to the system to be in stable position. Or in other words, we can say the additional gain provided to the system without affecting the stability of the system. So what about this phase margin? Wherever there is gain in gain margin, you have to replace as phase, which means the tolerance phase lag value given to the system to the verge of instability, or in other words, we can say additional gain provided to the system without affecting the stability. I can tell you this with an example. If I am considering the value of Kg to be 2 dB, okay, I can say 2 dB is the maximum gain value of the system to be in stable position. If the system exceeds 2 dB, then we can say that the system is be in unstable position. Okay, that is the gain margin. Margin in the sense it's limiting the value. So gain margin in the sense till this gain value the system is stable. Okay, so what about this phase margin? Till this phase value the system is stable. That is limiting the gain value and limiting the phase value to differentiate the stable from the unstable system. Understood? Now I am going to tell you how we are going to differentiate a system is stable and a system is unstable with respect to this gain margin and phase margin. For that, we need to consider 0 dB in magnitude plot and minus 180 degree in phase plot. So this is my magnitude plot and this is my phase plot. Here I am going to find out the intersecting point of 0 dB line and magnitude plot. So this is my intersecting point. I am extending this to the phase plot. In a similar way, I am finding the intersecting point of minus 180 degree and phase plot. So this is my intersecting point. I am extending this to the magnitude plot. In a similar pattern, I have found out the intersecting point of 0 dB line and magnitude plot, and I have extended it to the phase plot. Okay, and minus 180 degree and the phase plot intersecting point I have found out, and I have extended this to the magnitude plot. See here, gain margin value is below 0 dB. If the gain margin value is below 0 dB, then we can say the gain margin is positive. If it is above 0 dB, see this is my gain margin point. So if it is above 0 dB, then we can say the gain margin is negative. Similar way, this intersecting point meets the phase plot which is above 180 degree, I can say that it is positive gain margin, and if it is below 180 degree, then I can say that negative phase margin. So if we have positive phase margin and positive gain margin, then we can say that the system is stable, and if we have negative phase margin and negative gain margin, we can say that the system is unstable. Understood? So that's all about today's session. If you have any queries, please mail me. Don't forget to like, share and subscribe. Thank you.